Okay, should we get started then?
Let's do it.
Okay then. Hi, I'm Louisa Rhodes. I'm a water consultant at Arup.
And I'm
Uh,
Elliot Geen, a senior civil engineer at Arup as well.
and welcome to this online session, Too Much, Too Little, Too Dirty, How AI Can Help Respond to the Climate Resilience Challenge, part of World Water Week 2025. Today, we'll be looking at how we can use AI and predictive technology to help tackle the pressing issues across the water sector and create climate resilient solutions for the benefit of people, organizations, and the environment.
So this session will open with an interactive piece where you, the audience, thank you so much for joining online, can contribute to via Mentimeter to a discussion on what challenges you're facing and how you've used AI so far in your career or in your daily jobs. So if you would like to contribute, please have a phone or your PC to hand to join in the engagement. We will then see 4 different case studies, each one using AI in a different way to tackle a current problem. Throughout the case studies, we will have a Q&A portion of the Mentimeter open for you. So as you go along, if there's anything you want to ask, just chuck it into the Mentimeter, not necessarily into the chat. And then if you see a question that you particularly want questioned or answered first, please use the upvote option. And then we will put to our presenters during the Q&A section at the end. That will then take us to the end of the hour and our session today, but please do reach out with any of the presenters after the session for more information. Um,
Oh.
so myself and Louisa will be moderating the session today, and we'll start with some audience engagement.
So before we get to our case studies, we've got a Mentimeter. If you're not familiar with Menti, you can join online, go to that URL, menti.com, and put in the code, or you can scan the QR code. We'll give everyone a minute to join that, and then we'll switch to the Menti questions and see what you guys think. So another minute to join, and then we'll switch. Okay, so we've got some questions, we've already got some answers, but if you still need the join code, it's at the top.
This is great. So I guess question number 1 was where are your greatest challenges you see at the moment? So we've tried to, as of the title of this session, we've tried to group these into, is it too much water? Is it too little? Or is it too dirty? So yeah, again, it doesn't have to be necessarily something that you're actively working on right now, but just sort of where potentially you're trying to actively, you know, in the sort of focus area. And it's good to understand this as we move along in the session, maybe where we all stand. So this looks pretty even to me. But that's great. That's really, really good.
Nice, good to hear. So these are the problems you're facing, but uh, we'd be interested to know how you've engaged with AI so far. So what have you used? Is it just no, not engaged? Is it something like Copilot? Do you use specific tools such as neural networks, or just not sure? Maybe someone else, your organization does engage with AI, but you've no idea how. It's new to you. Um, Maybe there's a lot of not sures.
Yeah. I'm thinking, Louisa, here that I can see that there's at least 33 people here online with us, but
Aha.
only 10 answers. So I mean, are people struggling with accessing the Menti? If you use there's a URL at the top there, menti.com, and then you just chuck in that 8-digit number. We want to get as many of you guys in here as possible. Um, but do write in a chat if you're having issues or you're not maybe familiar with Menti. But we want to get as much in here as possible.
Nice. We got
So
some good responses. Um,
ChatGPT, I'm not surprised to see that one.
yeah.
What else have we got here?
Claude, ChatGPT, OpenAI. So a lot of LLMs or generative AI helps with, a range of things across businesses and organizations, bouncing ideas, generating new stuff, um, all sorts. Data analytics. Nice. Pollution treated. That would be interested to hear. Um, Specifically, maybe or maybe you're not sure exactly how you're using AI. Nice. Thanks,
How
everyone.
many responses we got? We got up to 12. Still struggling to get some more people in here, but that's fine. We do also probably need to move through with the program. Should we move on to the next
Yeah.
question, Louisa?
Yeah. So
Come.
if you have engaged with AI, have you seen a benefit? Um, maybe a lot, maybe a little, not sure. Don't know yet. No benefit.
Pretty neck and neck. I'm glad there's no answers coming through on the right hand side. Okay. We got in the Minty now. 13, it says. Um, this is positive.
Nice.
This is really, really positive.
Interesting that there aren't any not sure too early to say. I would have expected a few, but maybe people are already far
Maybe
down the
people have
path.
already, they're in this
Yeah.
session for that reason. They're already
Yeah.
using AI and they're already keen to see it, so they're not maybe on that not sure box. But yeah,
Yeah.
no, this is really interesting. Now we're getting up to 14 responses, 12 people. Um, like I said, if there's anyone online who's struggling, like I said, the link's at the top, menti.com, and then you just put in this 4-digit number, 8-digit number, sorry, because what will allow you once we get on from this engagement piece that during the presentation you can also ask your questions in there directly. So it's really important you guys get logged into Menti as we move on with the session. Okay, got 13 out of 14. Let's move on to the next question, Louisa. So here we're going to ask you, what kind of issues or barriers have you seen so far in trying to use AI? What do you think? We've tried to group these into sort of six buckets. Um, and feel also free to put anything in a chat if you don't feel like your bucket or the issues that you've come across are not here. I think we've also got the option that you can select more than one. If you think like all of these apply, then go for it. If there's one you feel more strongly about, that'd be great. It seems like, okay, straight away, security issues has jumped to the top. I'm not surprised to see that. Or data quality is also a popular one. Okay, it's balancing out. We've now got 17 people in the Menti. That's great. Keep on joining, guys. Remember, links at the top. Um, but yeah, security issues, that's a big topic or a big, let's say, issue or barrier. And this is really useful for us to understand. Because that's clearly a clear leader here in this poll. So that's really interesting to see. And also poor data quality. I mean, that's what we need AI to use, right? So that's got to be the starting point. If we need to get better, give it the best data it possibly can use, we're going to be stuck at sort of A1 or at the start of the challenge. So that's really, really interesting to see. Um, Has everyone what are the totals now? 15 out of 18. We'll give the last three people. We can't call you out, unfortunately, but if you can submit your submit, we get 18 responses here, that'd be great. Um, or if you feel, like I said, if you feel indifferent, if you don't think that any of these are the issues, please put them in the chat as well on Zoom. That'd be great. But yeah, really, 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 really interesting. Thanks for putting in your answers, guys. Louisa,
Yeah.
should we move on to the next stage, the next
Yeah.
task?
So that was our engagement for the start, but we're going to leave the Menti open for the rest of the talk. His Facebook questions to any of the speakers on any topics. But you can also upvote other people's questions if you see one you particularly like answered. We're going to leave this open. You can keep using the code to join and put your questions in here. Have a look at the ones. So we're going to go back to the main presentation now. Um, and we're going to jump into our case studies.
Great. Thank you, Louisa. So I'll start on our first case study. So, like we said, the title of the session you guys are all aware of: too much, too little, too dirty. Our first focus is going to be grouping where the applications of AI has been used in the too much sector or the area. So we're going to start with flood AI, tackling the problem of too much water in the form of flooding in Northumbria, UK. This case study will be presented by Nick Watson, who is a flood and coast erosion risk manager at Northumberland County Council, and Kat Wallace, a senior civil engineer at Arup. Over to you both. Thank you so much for joining.
Thank you very much, Elliot. So we'll be talking about the problem of too much water, and in particular, when you get too much water too quickly, and how we're looking to address this with Flood AI. So for a bit of background, Flood AI is part of DEFRA's, it's a project funded by DEFRA, DEFRA being the UK government body with an overview of flood risk management. DEFRA realised that it's not going to be possible as a society to keep preventing flooding by building defences, and so there's an acknowledgement that actually we do need to focus on resilience, hence the Flood and Coastal Resilience Innovation Programme, looking at ways to innovatively improve resilience across the country. So through Flood AI, we're looking to pilot an innovative flood warning system using AI and machine learning in 6 pilot communities across Northumberland that aren't currently served by flood warning services. I think our vision statement there sums it up really nicely: to enable greater flood resilience in 6 communities by delivering technologically innovative and enhanced flood warning systems. And the key bit really here is capable of providing specific and timely warnings in mid and fast response catchments that currently aren't served by flood warnings. So the next slide, please. So the challenge that we're looking to address is that there's 2.5 million properties at risk of river and sea flooding in England. And if you include flooding from ordinary smaller watercourses, that would actually be even higher. Lots of these communities are served by flood warnings, but lots of them aren't. And this really particularly affects fast responding catchments. So where there's rural communities, urban communities with these smaller, flashier, fast responding catchments that are becoming even more of a problem with climate change. These communities currently can't be served by flood warnings, largely due to the technological challenges with existing flood warnings. A really unfortunate example is Acomb in Northumberland in the UK, where last year there was a flood warning system in place, but unfortunately the flood warning was only issued after the flooding had happened, which is really reflective of the issue that the current technology, the current hydraulic modelling process of predicting flooding is quite time intensive. So we're really looking to address that with Flood AI. And just to really drive home the message of why this is important, without flood warnings, communities, that's residents and responders, so the organisations that respond to flooding, aren't able to understand that flooding's coming. They're not able to then take action to prevent damages to property or people, left vulnerable and unable to effectively respond. So we're really looking to be able to provide these communities that aren't currently served with flood warnings with really specific and timely information to allow them to respond better. Over to you, Kat.
Thanks, Nick. So why should we consider AI for this challenge over traditional physics-based models? Firstly, I wanted to talk about accuracy. With the right training data sets, evidence suggests that AI and ML models can be delivered for flood forecasting purposes. While we might not have seen the severity of the flood event in that exact catchment before to have the perfect training data set for it, it's important to remember that we're asking if the water will be ankle deep or knee deep, not for millimeter precision. AI ML can definitely provide this. However, the key driver for AI ML in flood forecasting is more so their efficiency. They take a matter of minutes to run rather than the hours or days traditional models can take, which opens the doors to data-driven operational responses, which otherwise just can't be accessed. These models can also be incredibly flexible, making use of increasingly available large remote sensing datasets, such as rainfall radar and nowcasting solutions. They're also very scalable to new catchments as the build process is very repeatable. Next slide, please. So how does it all work? Essentially, AI and ML models the relative behavior of point locations within the catchment. In its most basic sense, it's learning the relationship between rainfall in the upper part of the catchment with the water level in the community at risk. They're not modeling the physical water molecule as it moves from A to B, like a physics-based model does. It's the relative behavior and the relationships that they're learning. As part of the project, we're utilising 3 types of sensors to train the models, including rainfall and water level, as well as trialling the use of soil moisture. The use of soil moisture is part of the project's innovation, and we're hoping it can help us differentiate between the behaviour of winter and summer storms, which are becoming increasingly common. AML models do require 2 to 3 years worth of data to train, normally in the way of sensor data, but we're trialling the use of remote sensing datasets to reduce maintenance and resource and costs associated with this. Our model output is currently a forecast hydrograph at a point location within the community at risk, which can then be used to inform flood warning or response coordination. Next slide, please, Louisa. In terms of project progress and model performance, Flood AI is just concluding its alpha phase, which is where we've built our proof of concept models for 2 of the 6 pilot catchments. As you can see on the right-hand side, we're having considerable success forecasting in these catchments. However, these proof of concept models currently use perfect rainfall, which is essentially observed rainfall being drip fed as if it was a forecast. But given that our communities flood within about 20 minutes of the rain falling and that we're trying to provide a few hours worth of warning, we need to transition to using rainfall forecasting, which is inherently uncertain. How we map this uncertainty propagation through our models and communicate it to our users will be a key aspect of the next phase. Once these models have been enhanced, we're looking to start a more rigorous testing period in the new year with operational response authorities and communities alike. Next slide, please, Louisa. Looking to the future of flood forecasting, I think it would be really interesting to pair our AI/ML models with a 2D inundation solver, with the AI/ML providing the boundary conditions to this much smaller physics-based model. This could be a really powerful combination, providing significantly more opportunity than either could provide by themselves. We could provide responders with flood outlines and hazard mapping, potentially even with mitigation options such as deployment of demountable defences, all in real time. Solutions like these have the potential to transform how we respond to flooding in a resilience context, and I'm really looking forward to seeing what we can achieve with them. It's back to you, Elliot.
Thank you, Kat. Oh, go on, Louisa.
Thanks so much. No, all good. Thanks, Kat and Nick. That was really interesting to hear about how we're using AML to solve problems for people in these vulnerable places. Our next case study is also on the topic of too much water. It's around addressing infiltration and ingress of additional water into sewers. It's presented by Mads Damsgaard Hansen, who's Chief Commercial Officer at Infertiles. Over to you, Mads.
Thank you, Louisa. So yeah, thank you and welcome all. As the previous slide just showed, this is a case study from Norway, from one of our utilities called Lillestrøm. We do have this solution live working in 6 different countries in Northern Europe, mainly Norway, UK, and Netherlands. So this is a problem that is not only, say, local for us in Norway, but something that is relevant for everyone. So shortly on inflow and infiltration, if you just change the slide, Louisa, just to make sure everyone is up to date, what inflow and infiltration, or I&I as we say, actually is. Basically, it's water either infiltrating the sewer through cracks, as the one showed on top, and inflow is rainwater or other surface water coming into the sewer through the say correct channels. But the challenge here is that 40 to 50% of all this water in the sewer shouldn't be there. So that's the infiltration, and due to that large amount of infiltration, there's a massive reduction in the capacity of the sewer. And that leads to a lot of overflows and flooding and spills when we see some of these more and more increasingly heavy rainfalls that appears. So there's a lot of consequences here from having the I&I. And furthermore, there's also the energy situation, because the more inflow, the more infiltration we have, all of this basically clean water needs to be pumped and treated. And that's costly both in terms of electricity use, use of chemicals and treatments, and also, of course, the carbon footprint. Next slide. So what we have developed here is an AI ML solution we call Sewer Intelligence. And what it does in short description is that basically we enable the utilities to upload, or we connect live with all of the necessary data that is available. So that's all of the GRS network data, all the SCADA data, everything. And we basically allow our utilities to go from the first point, which is connect or upload data, to actually visualize and have a proper overview of the INI within a matter of, say, 4 to 6 weeks. So using AI, we speed up this process, which usually takes years for most of the utilities to get to. We actually do that in a matter of a few weeks by the use here. And if we can go to the next slide, one of the key elements here is what we call PyFusion. And in short, PyFusion is an algorithm where we, based on, of course, the utility's own network data, but also all of the network data that we have from previous clients. So we're talking hundreds of thousands of kilometers of network data, where we run this AI algorithm that basically enables the utility to get a full digital correct version of their sewer network. And having a full correct model of the sewer network allows the analysis afterwards to be much more accurate, because now we know exactly how everything is connected in the catchments, how it reacts in different scenarios. And this understanding is very crucial in order to perform modeling or analysis or anything else afterwards. And the algorithm is both cleaning the nodes, the ends, the flow directions, material type, age. Everything is done with a statistical accuracy that is 99% accurate, and leaves the utility with a set of data for the GRS that is that has been increased a lot in terms of the quality going forward. Next slide. So once we have done this analysis of the GIS network, we then apply all of the data that is from the SCADA system. And as we saw in the voting just before, some of the most critical areas was lack of data or data quality. And what we do here is, first of all, we increase the data quality with the PyFusion, so that barrier has now been, say, removed. And we then apply all of the existing data that is available via the SCADA. So the SCADA from data from pumping stations, flow meters, everything that is already readily available, we use in this analysis, because often there are hundreds of thousands of different data points that we can already use without having to install more and more meters, because this is an agnostic solution. It just requires the data basically. And when we then apply the data analysis and the AI analysis on top of the PyFusion outcomes, we enable, first of all, to get a full understanding of each of the catchments, understand how much INI is coming, what is infiltration, what is inflow, the quantity, and of course also the location, because having INI is something that we will never get to zero. That's not the point of this solution. The point of this solution is to optimize the interventions needed by the utility. And as I'm trying to mark out with a little black circle around the red pipeline area, we enable, through this INI solution, to help the utility understand exactly which pipes are causing the problems. So where to start mitigating the INI, because which ones are causing the major problems, and having thousands of kilometers of sewers, in this case 2,700 kilometers, you might only have to change a few kilometers of pipes, and then you're actually clear of the target and are not getting any more spills, etc. So that is, in short, what we use this AI solution for. And by using these vast amount of data, we are able to point out the results much more accurate than than any other of the users in the utility, because statistically we know how correct we are when pointing to the areas of the INI. So no more guesswork, but use the AI to analyze and validate all of these millions of data points to get accurate outputs. That is in short, what we enable the utilities to through the use of AI. I think that's my 8 minutes-ish.
Thank you so much, Mads. That was really good. I really enjoyed that. I mean, I come from a wastewater sort of background, and having the ability to quantify this excess flow in the network using AI is really, really powerful. And I think it lies nicely with this whole too much problem, too much water getting in. And then you've given a real life example here from Norway of how you've used AI to basically combat that. So that is really, really interesting. I think what we're going to do next, if I'm not mistaken, Louisa, is moving to the other side of the spectrum, too little. So where do we see a case study that is centered around too little? So I have the pleasure of introducing Luciana from our office in Holland. So she is going to give a presentation on how we approach future water scarcity with a case study on low flow water networks. Please, Luciana, go ahead.
Thanks, Elliot. Good afternoon, everyone. Today we'll look at why conserving water, while essential, is also transforming the way we must design and operate our urban water, drinking water, and sewer water transport networks. So too little. Globally, by 2050, 3 out of 4 people could face water shortages. And in the UK, particularly, we are looking at 5 billion liter a day deficit by 2055, and that's a lot of water. That is equivalent of everyone in the UK forgetting to turn off the tap for approximately 5 minutes a day. On the other hand, UK government plans to build 1.5 million homes in 5 years. So one hand, more people, less water. You don't need to be an engineer to see that the math doesn't add up. So water conservation is really crucial. Could we move to the next slide, please? Yes. And water conservation is being driven by a mix of technology adaptation, behavior, and policy. Looking at high efficiency appliances, they reduce daily water use significantly, saving liters of water with every flush or wash. Grey water reuse, on the other hand, rainwater harvesting help households step into local and non-potable water source. Smart metering and demand management are helpful for water utilities to spot the leakages, but also for people and communities to work on behavioral change. And finally, regulation provides the push, ensuring conservation is not left to chance, but becomes a standard across communities. Could we move to another slide? Next slide, please. And when less becomes a challenge, while water conservation, as explained, is essential, it can create unexpected challenges. Looking at the drinking water networks, low water use on a household level means that you will have lower flows in the oversized networks. You will have stagnation, less velocities, low velocities. In chlorinated systems, you might also have loss of disinfectant residuals and also overall water quality issues. Looking at the sewer systems, you get different type of water, wastewater. You get thicker water, which would move slower. You can get sediment buildup, odor blockages, and higher pollutant concentrations, which will again have an impact on treatment works, more concentrated water influence, different temperature, and altered hydraulic loading. Next slide, please. So unfortunately, there's a mismatch between past, present, and future. Our current design criteria are still based on historical higher demand, and the engineers usually overlook water efficient housing and oversized assets in low demand constants that is just a wasted capacity. And in most of the cases, self-cleansing thresholds for velocities and flushing rules may no longer apply. So we need to change these criteria. Can we move to the next slide? So to bridge this gap, we will start a project where we will develop an integrated model for drinking water and sewer networks. So on the left, what you see that we will start from a household behavior. So how long people shower, how often toilets is flushed, when taps is used. So we will generate these demand patterns using a software called Symbiome, which is able to generate stochastic demand patterns on a very small temporal and not also temporal, but also like a tap level. So different taps have different demand patterns, and we will implement these patterns into hydraulic softwares. You can use whatever software you want, but we will use InfoWorks, Water Supply Pro, and Integrated Catchment Model, ICM. And this scenario, we will test different scenarios, reuse scenarios, and we'll try to validate our model based on the current situation with about 4,000 households. Next slide, please. And with this model, we'll test, as said, various water reuse scenarios, and we will, in a nutshell, try to develop new design criteria. So we will translate modeling insights into the future design criteria, which are like pipe sizing, what slope we need to set, and what are the flushing criteria for both drinking water and sewer systems. And these criteria, this is the most important part, that we will co-develop these criteria with utilities and planners and developers, so that these criteria can be really used. Next slide, please. And last but not least, we will try to include AI as a design partner, because with AI, we can find the best performance design solutions. We can set maybe adaptive thresholds instead of like cleansing velocity of 0.4. We set it per region where the pipes are and the diameters of the pipes. So dynamic rules, not the static one size fits all. And we will maybe also include machine learning to predict stagnation blockages and other hotspots. And to conclude, this project will look ahead how low demand future water conservation reshapes the way our drinking water and sewer system behave. And by combining modeling, scenario testing, and AI, we aim to create guidelines that will keep our infrastructure future-proof and efficient.
Thanks so much, Liana. That was great to hear about how you're working to tackle the problem of too little water, where others have too much. We're seeing problems across the spectrum. Our final case study is on the topic of too dirty. So we've seen too much, too little, now it's too dirty. We're going to hear from Vicky Williams, Digital Water Leader Arup, discussing inlet water optimization of water treatment works. Over to you, Vicky.
Good afternoon, everyone, and welcome to the session. This bit is about the too dirty part of it. As we can see with changes in climate, that we don't always get the water that we're expecting into our treatment works, and therefore this project was looking at and thinking about what do we do when we see different types of water quality coming onto the treatment works. If you could go to the next slide, Louisa. I think one of the challenges that have been set out in the UK water sector, so not just dealing with the dirty water, but thinking about what kinds of additional treatment technology that we have to put on our water and wastewater treatment works, and thinking about the embedded carbon impact on that as well from a climate resilience point of view. Water companies actually in England made a public interest commitment to reach net zero on some of their operational emissions. And quite a lot of that focused on how do we get to zero efficient wastewater treatment works. But here we want to not forget our water treatment work process emissions as well, and make sure that those things are coming into effect. And what happens in this hypothesis? What happens if we could get to a position using machine learning and AI to only treat the cleanest water possible? Some of the roadmap that we're seeing now, Water UK is the body responsible for the think tank. It represents the UK water sector, and they've developed a net zero roadmap containing 6 industry commitments. And one of those is to start looking at what the impact of process emissions are on CO2. And just to give a scale of this, the water sector in England and Wales has process emissions estimated at 3 million tonnes of carbon dioxide equivalent per year. So it's quite a substantial thing to think about when we ever increasingly have to deal with dirty water, put on more process technology, and therefore actually the cost of running those technologies goes up. So the question we're posing here is, could the use of digital technology around machine learning and AI help us make those processes as efficient as possible? If you move to the next slide, Louisa, thanks. So this case study centres around a lowland river catchment and a treatment works that sits on the River Stour. It's a 45 megalitres per day plant, and it struggles with pollutants, particularly linked with adverse weather conditions, and they are quite reasonably hard to treat water quality parameters, in particular nitrates, pesticides from the agricultural lands, and also that it has to deal with significantly with algal blooms during some of the periods of warmer months. And so what this does is it reduces the capacity on this particular treatment works on the Stour, so it's unable to ever reach the production level that's required. And having just heard on Liliana's presentation too little, water companies really do need to reach the extent of their production before bringing on new sources. Next slide, please, Louisa. So when we set out to build this model, we had to think about what are the attributing factors that might be in here. And this slide sort of represents all of the different elements that we decided to do, because we didn't just say, oh, we're building a model right now. What we had to really do is understand the catchment information that fed into this treatment works and develop these decision trees around the decision making that the operators would use on the plant. We needed to look at how the historical abstraction decisions were made and the pathways for those decisions. And also looking at things like how the treatment work, how they operate the treatment works, and then also bringing together what we thought were relevant data sets that could come into the data analysis. And some of them you can see down there are soil moisture deficit, telemetry data, water quality data, rainfall data, and temperature. And this allowed us to then start to think about and test different types of models. So we didn't just want to go with 1 or 2 models, we wanted to trial a number of models. And I'm going to show you a snapshot of some of the results that we've got here, looking at very specific parameters that came out. If you could look at the next slide for me, Louisa. So in this one here is the model that we selected in the end is one of the recurrent neural networks. We found that this was one of the best ways of looking at these different parameters. And this one, I'm just bringing out here the parameter of nitrate. And nitrate is really a good parameter to predict because it's highly soluble in water and quite stable. And we could look at the ways that application of nutrients were added to fields and how this river particularly behaved. So when we started plotting historic data, you could see the nitrate peaks being very characterized, and you could see them over time. So what we wanted to do is look at some of the explanatory factors for why we would get those different peaks. And one of the amazing kind of discoveries, which isn't obvious when you think about it, was quite how impactful soil moisture deficit is in terms of nitrate concentrations. And it's influenced by temperature, surface radiation, and rainfall. But it made a difference in terms of the predictability of the model. And also one of the areas looking at is rainfall is actually the primary factor in nitrate concentrations, which would make sense. You get some intense rainfall, it falls on the land, how quickly it goes into the river, and then when it arrives at the treatment works. Next slide, please. So these are the outputs of the model when we tested it on the prediction, and we could predict, we started to build in predictions up to 2 days advance. And you can see here in the graph on the left is quite how impactful soil moisture deficit was in our model predictions. But also the outputs of this model is we use R² as a statistical describer of how good and correlated the model is. And here we're getting a 0.95 prediction, which is very good for nitrate. And it showed that the recurrent neural network on this was really strong. This was much stronger that we found. I'm presenting you the nitrate results here because it was much more strongly correlated for nitrate than some of the others, like pesticides and algal blooms, where there were other influencing factors that needed to be added in there to refine the model. But in terms of nitrate, we should regularly think about how we might keep predicting this hard to treat parameter in river water quality, because if we could actually turn off the treatment and store water rather than letting it come onto the site, we could potentially avoid having to invest in costly nitrate treatment removal. Next slide, please. This is a model that we tested during this particular project, and one of the things I just wanted to kind of here sort of represent here is the first model was about, can we predict ahead? But we used what we call the Facebook profit model, and what it was is it was not very good in kind of suggesting kind of predictions in a short-term order ahead. But what we found with this particular model, that we could track changes over time and seeing if we're getting improving or worsening performances in the catchments. And here on this model, we could see over quite a substantial time that we were getting a general trend of upwards of increasing nitrate levels that were coming from this particular catchment. So either there was more nitrate going on the land, or it was the climate meant that it was reaching the treatment works faster than it is. And what this type of modelling would be able to do is to help utilities plan ahead and say, when do we need to bring on different treatment works, or operational have different standards because we're going to breach the standard in certain time. So I think it gave a helpful nudge to the water utility client that helps to support their business cases for investment in new infrastructure. And then if you could move on to the next slide. So in terms of what were the outcomes of this project, I mean, I think we could clearly see that our model forecast allowed us to predict nitrate and algal blooms at this specific works 2 days in advance. And what this is designed to be is it doesn't replace any SCADA or any type of technology that operators would have on their site, but it would be an accompanying toolkit to allow them to understand what was happening in the catchment and to make suitable operational decisions in advance. And that could be bringing on additional water sources, or turning, bringing on treatment, or helping to potentially plan their maintenance. So one thing that we said is this would potentially, by looking at this optimizing of the load onto the site, it would then enhance and increase process certainty. And so the conclusion to say is we would be able to then start putting together business cases to look at the most energy efficient and carbon efficiency of some of the water sources that we were using. We could bring on storage capacity and mix river intake with other different types of storage that this particular plant could do. And we could look to try and get a consistent nitrate load onto this specific treatment plant. And that's me. I think I'm out of time. I'll hand back to Louisa and Elliot for the next bit of the session. Thank you.
Thanks so much, Vicky. That was really interesting to hear. We're going to move to a Q&A now. We can have questions for any of the presenters, any of the teams. But I think we'll start with one for everyone, a bit of an open question. We've seen 4 different approaches to using AI and digital tools to respond to the climate resilience challenge. Open to anyone, what do you think are the benefits of AI and these data-driven methods over existing or traditional approaches? Where does it really shine for you? Or maybe where does it not work so well and we need to work on? Anyone's welcome to comment on that.
I can take that one, Louisa. At least give my perspective. I think for us, it's about the vast amount of data that is actually out there that is impossible to figure out with the human mind what is actually right or wrong, if you will, because of those vast amounts. So for us, it's about the AI really comes into play when you're able to, first of all, sort the data, of course, to make sure that the data you use is correct, and then from that perform the analysis again and again and again, because it's not just a one-time picture, it's something that usually is run every minute or every hour or every day. So using AI to enable that and help the operators not to do the decision for them, but to basically take it from maybe hundreds of thousands of different solutions down to the top 1 to 3 best ones, and then from that make a decision. That's I think where AI comes into play. It helps us use all the metadata that we have been a buzzword for the past 10-15 years.
Fantastic. Thanks. It's really interesting to those reflections. We've got a question from the audience as well. This is for Flood AI. Given the complexity of heavily modified river systems, which we have all over, where flow is regulated by weirs, pumps, sluices, all that kind of stuff, how adaptable is Flood AI? How adaptable is Flood AI to simulate flood scenarios with those systems in place?
Sure, I'm happy to take this one, Nick, if you want. Yeah, so as part of the Flood AI project, I guess we've been looking at kind of those smaller watercourses as in kind of rural areas, which you're right, they don't have many of these kind of structures in them. However, kind of where our initial exploration, I guess, of this technology and techniques, we actually started in kind of sewer networks and things, and looking at sewer flooding, which do have many more of these, and the tech's applicable to both effectively. Where the system is a little bit more complex, I guess, that you need to kind of support the models with a bit more of that engineering judgment and things, and bringing that in for you. So just taking an example of that, you've mentioned pumps as a specific one. So if you had like a water level in a sump that was being fed into your model, for example, like a linear machine learning model wouldn't be able to pick up the relationship that's there, and it wouldn't be able to particularly learn from it. However, as soon as you can, like, if you turn the water level within the sump into a rate that it's changing, for example, that then becomes significantly more helpful, and there is a linear relationship there that the model can learn. So that's one type of model, but there are many other types of models, some of which are a lot cleverer than that, but need more data effectively. So long as you've got some data and you can put that in a way or manipulate that into a way such that it's right for the model that you're using, they can definitely be applied to those situations as well. I hope that answers the question.
Fantastic, thank you. Yeah, if anyone would like to follow up on the question as well, please just raise your hand or pop it in the chat. We've got a question for Mads on INI. Do you need a lot of data to help create INI models? What happens in low data conditions?
Good question. It's a yes and no. We don't need a lot of data because, as I said, usually the data already available in pumping stations on flow meters and in SCADA system is more than enough for us to use. But if we have only encountered in one case where all of the network was based on gravity, so no pumping stations, no flow meters, etc. We use the existing analysis that we do to pinpoint exactly where is the optimal use and placement of sensors to get more data so that we get to the accuracy that is needed. So if we don't have enough data, we use the analysis to point out how much more hardware is needed to get the data that needs to be sufficient for a precise analysis. So we use that to save money basically for the utility, not buying thousands of new sensors, but maybe saying if you place sensors in these 100 locations, you have enough to get to the analysis.
Well, thank you very much. There's a more general question, but I think it's closely related to Liliana, your work on using AI as a design partner. The question is simply, do you think one of the best uses of AI is to speed up decision making? I suppose if anyone else also wants to comment on that, it's quite a broad question.
Broad question, but eventually we would like to include it. First, to make an inventarization, which methodology to apply, and then screen for the best solution. But definitely, I would like to have if we have enough data. So I would like to have machine learning for prediction of blockages in sewer systems, but also maybe machine learning for prediction of chemical and microbial water quality in drinking water systems. So, but that depends on the data set that we will get from the water company that we are working together with, and that is Anglian Water. So depending on the data set that we can get from the water utility, we will then make a decision which AI methodology we will apply.
Thanks. Good to hear. So we've got a question for Vicky on the water quality AI model. Do you take into consideration the nitrification phenomena, the oxygenation of the river?
For this particular model, we didn't, and for the reason being is it's quite hard. It was quite hard to get any data sets from, particularly of quality data within the river that gave us enough of the data around the nitrification process. And actually what we were really interested in, where we took the data from, where we had lots and lots and lots of data and quality data, was from the inlet to the treatment works. So in essence, we were just looking at characteristics of the catchment around things like weather data and application levels and soil moisture deficit, and looked at how it predicted what the actual nitrate level was into the incoming inlet of the treatment works, because that's actually what the treatment operators cared about. And so because we had 10 to 12 years of data, we were just looking for pattern recognition around that over time. I think the one thing to say on this is that the way we trained the model was to train it up till on 10 years worth of data, but keep 2 years worth actual back and don't put it into the model, and see if it did predict with some degree of accuracy the data that we actually got. And that's what the model actually did. And unfortunately, this didn't continue because we were trying to see could we put this into operations and run it continuously around the thing. But the project was unable to get funding to kind of continue. So it still remains a kind of thing that we've got to do. So yeah, so in short answer, no.
Okay. I've got a question for Kat and Flood AI. Can you expand on joining AI/ML to 2D inundation models in terms of producing fast and readily available data?
Sure. So one of the reasons I guess we're looking at that in a bit more detail. So as I mentioned, the AI/ML models, our output is like a point location hydrograph. which gives you so much information. But there is no like training data set as such to link that to the 2D domain. So if you're talking about flood extents and things, we don't really have the training data sets to train the machine learning models to do that kind of thing, which is where linking it back to a physics-based model then kind of opens the door to that sort of thing. So that's why the connection, I guess. In terms of the fast element of that, and so by having the machine learning model creating the boundary conditions for that much smaller model, that will kind of help with that speed element, I guess, and you're not trying to run then a massive physics-based model that you kind of otherwise would have to do. But you can kind of create your boundary conditions much smarter. There are also kind of other light touch kind of 2D inundation models that we're exploring use with that are kind of a bit lighter than the kind of traditional design models that get used elsewhere. So yeah, I hope that answers the question.
Fantastic, thanks. We've got a couple of questions in the Zoom chat for the two little water speakers. So Liana, if behavioral change is needed, do you have solutions for monitoring at household level? That is things individuals can do to help.
Can you repeat the question? I'm sorry.
Sorry, if behavioral change is needed, do you have solutions for monitoring at a household level? So are there things that individuals can do to help?
Yeah, solutions, maybe smart water metering can be one of the solutions. Then the household members could actually see how much water is being saved. And but I think policy pushes would be the most critical one. These are like the problem with water is it is too cheap. If it was electricity, then it would be behavioral change during, for instance, the crisis a couple of years ago here in the Netherlands, when gas price went up and electricity price went up, everyone started showering less. So water was also saved. So I think the price of water is the main blocker because it's too cheap to be saved. But I think with policy shifts and new policies, and that can really help. But on a household level, people should just be aware of water shortage, should turn off the tap while brushing teeth, turn off the tap while shampooing hair. So all these small, or reuse some water for gardening. So just try to be just eco-friendly, and water will be saved. But with small things, you can actually have a large impact on the whole system.
Sounds
Thank you for
good.
your answer. Thanks, Leah. I'm thinking, I'm conscious of time. This Q&A has been really good, and thank you so much to our presenters as well for giving their bursts, and for you guys online for putting in your questions in the Q&A. So like I said, if there's anything you would like to follow up on, please feel free to reach out to any of our presenters. Their names are here. We would love to hear your thoughts or any further questions. I appreciate we might not have answered all of them, but I think I'm just going to try and wrap up the session now with the 2 or 1 minutes that we have left. So yeah, we hope that you've come away from this session with a sort of an idea of how AI is now currently being implemented around the world in tackling the problem of what we just discussed: too much water, too little water, or too dirty water. I think especially when we've got this big challenge ahead of us, centered around climate resilience, this is really sort of at the forefront of what's being hopefully coming forward. So to try and wrap things up, I'll hand over finally to Louisa, but thank you so much for joining.
Thanks, everyone. Thank you, everyone, for joining. We had a range of case studies tackling these problems, and feel free to reach out to any of our presenters. We hope you have a great day and enjoy the rest of World Water Week 2025. Thank you very much.
Thank you all.
Bye.